Hello, everyone. Welcome to a new lecture of our course on heterogeneous systems. Today, we are going to talk about an exciting topic, collaborative computing or collaborative heterogeneous computing. We are going to learn and discuss how to implement optimized programs that take advantage of the best of different devices in the same system. We will mostly focus on systems with CPUs and GPUs, but we'll also talk about systems with CPUs, FPGAs, and we'll mention also other heterogeneous devices. But before we go into the details, let me very quickly remind you what we covered in our previous lecture. We talk about dynamic parallelism, that is interface that GPU programming frameworks like CUDA and OpenCL provide to express dynamic parallelism or dynamic refinement algorithms in a more natural way. We discussed like what are the important semantics when using CUDA dynamic parallelism, and also discussed important performance considerations. Remember that when you write a program without using dynamic parallelism, it's the responsibility of the programmer to figure out what should be the execution configuration every time that the host launches the kernel for execution on the device. And this may be painful to program. With dynamic parallelism, it's easier to take advantage of dynamically discovered parallelism because threads inside the GPU device are able to launch new kernels by themselves. If you want to recap on what we covered in the previous lecture, here you have a link to the recording. So let's start talking about collaborative computing. We have actually talked already about collaborative computing in a previous lecture, in particular in the lecture about graph search, where we presented the BFS algorithm, the breadth first search algorithm, and we talk about the fact that in BFS, small size frontiers may underutilize the GPU resources. If you look at this plot that we have in the slide, you see that for the different frontiers over the execution of the BFS algorithm, every time that we iterate, we have a new input frontier, and depending on what's the size of this input frontier, the CPU or the GPU might be better for execution of this frontier. And this essentially relates to the size of the frontiers, the number of nodes that we need to explore in every iteration. If you look at the plot and you see the initial iterations and also the final iterations where we are, let's say, at the extremes of the graph when executing the BFS algorithm, you can observe that the CPU is faster than the GPU for these frontiers, right? While we are here in the middle, we see that the GPU is significantly faster than the CPU because there are many more nodes in this frontier, so there is much more parallelism. So we choose the CPU or the GPU depending on the frontier. In this sense, we are going to have a limit or a threshold to decide when to use one device or the other device. We will see today different ways of implementing this scheme, starting from the most basic one without unified memory and without relatively new programming features that we have available in CUDA and OpenCL programming frameworks. And we will go to more sophisticated implementations that take advantage of these new features. And here you can see, remind this slide where we see what are the final results for two different graphs. Here we normalize the execution time to the execution time of the CPU only version, and we compare the execution time of the collaborative CPU or GPU version and the GPU only version. As you see, we can achieve up to 15% improvement for performance improvement for this graph. So if you want to recap on graph search, you can take a look at the lecture that we delivered a few weeks ago. But collaborative computing is not only restricted to very few examples, such as the one that I just gave you on an NVIDIA Jetson platform. It's hopefully a much more promising trend. And these days, very recently, we heard about the announcement of the new NVIDIA Grace Hopper superchip that integrates CPU and GPU. It's a great CPU that is ARM-based CPU. We will briefly talk about that later in this lecture, and also a Hopper H100 GPU. Interesting thing here is that these two devices are tightly connected using a 900 gigabyte per second coherent interface. As you can see in the slide, this is 7 times faster than PCI Express generation 5. And this is extremely interesting for collaborative computing workloads because it's going to allow much faster communication, synchronization, and also data sharing between the different devices. So we are going to talk about how to implement a collaborative execution or collaborative heterogeneous implementations of our programs. And to do so, we have to learn the basics of the unified memory system that is the one that really enables this tight collaboration between different devices. So let's start talking about the unified memory. But before that, let me very quickly remind you how we used to communicate CPU and GPU in an heterogeneous system with CPU and GPU. Remember that we have to do memory allocation on the GPU memory by using CUDA-malloc, if we are using CUDA as a programming framework. And we also have to explicitly transfer data from the CPU memory to the GPU memory, and also results from the GPU memory to the CPU memory. So that's what we normally call the accelerator model that naturally matches systems with discrete GPUs. So here, just to remind you very quickly how we would do this, or how we would code this. We first allocate input data on the CPU memory. We also do the allocation on the GPU memory, and we transfer the data from the host to the device. We can also allocate for the output, both in the CPU memory and in the GPU memory, and then we will launch the GPU kernel. We may want to use this CUDA device synchronized, especially when we are using asynchronous transfers, and at the end we will copy the output from the CPU memory to the from the GPU memory to the CPU memory. So with unified memory, we have a unified virtual address space where the same virtual address space, the same addresses are or can be shared by the host and the device, by the CPU and the GPU if we are in the context of GPUs. This idea of unified memory started to be developed in CUDA 6, but at that time, the size of the unified memory was limited to the GPU memory size. After CUDA 8 and the Pascal architecture, now the only limitation for this unified memory is the system memory. And the key advantage of this unified memory that appears with CUDA 8 and with Pascal is that the GPU has the ability to execute page faults. That means that the GPU can oversubscribe, can access data that doesn't reside physically in the GPU memory, but it can perform a page fault handling procedure, communicate to the CPU that is missing a specific page of size, typically 4 kilobytes, and the DM8 engine on the CPU side will perform the transfer of this page to the GPU memory for the GPU threads to use that data. This concept of unified memory is not only invented in CUDA, it also appeared at the same time, more or less, for other architectures as well. It's what we call, or what they call, the heterogeneous system architecture that, similarly to the unified memory in CUDA, extends the unified memory space beyond GPUs, and not only GPUs, but also other accelerators like DSPs, DMA engines, or crypto engines. So compared to the legacy system where the different accelerators are connected through some sort of bus, for example, PCI Express, even in when there is a physical integration, when both CPU and GPU are in the same chip, or even in the same package, they were, in these legacy systems, were using even the same physical memory as if they were two separated memories. However, with the HSA architecture, it's possible to have this unified, coherent memory space that is the same virtual memory space for all the different devices in the system. Here in the slide, you can see CPU cores, GPU compute units, or DSPs. So regarding the memory management in the unified memory, one key observation here is that one of the biggest advantages of the unified memory is that programming is much easier. Essentially, because now we don't have to double allocate anymore in CPU or in GPU, and also perform explicit data transfers between CPU and GPU. We can use a single API. In the case of CUDA, it's called CUDA malloc manage, and by using this CUDA malloc manage, and even though here we are also still allocating separately the input on the CPU memory, but this CUDA malloc manage is in the unified memory space. So that's why we can, for example, use a regular mem copy to copy the input that might have been generated or loaded from a file into the shared memory space. So, and then we similarly can allocate the output. And one key difference that you can observe now in this code is that we can even launch the GPU kernel without performing any explicit transfers. In this case, we for sure have to use this CUDA device synchronize, because it's the way to make sure that the GPU kernel finished and the CPU or CPU threads can read this the output. So in summary, there is no need for double allocation or data transfers. And if you think about it, this model naturally matches physically integrated devices like CPUs and GPUs in the same chip, or devices in the same, using even the same physical memory, maybe not the same chip, but in the same package. But still, this can also be implemented for discrete GPUs, and this CUDA malloc manage is available to essentially all NVIDIA GPUs these days, regardless of whether they are integrated or discrete. So if you want to see a little bit of the performance that the unified memory can provide, because that's also important, as you can imagine, handling all these memory allocations, data transfers, page faults, without any programming intervention might have a certain overhead. And actually, we did some interesting analysis comparing different benchmarks, and we will talk later about these different benchmarks because they belong to the Chai benchmark suites. And here you can see on an NVIDIA Pascal GPU a comparison of these different benchmarks for the discrete version, let's say using the traditional accelerator model, and this unified memory that take advantage of the unified and the virtual unified virtual memory space. So as you see, for some of these workloads, there is essentially no difference in execution time, in kernel execution time, when we compare the discrete and the unified version, because for these particular workloads, there is no cross-device communication. So once we have accessed data for the first time and we have moved to the GPU memory the necessary data, there is no further interaction between the CPU and the GPU until the end of the kernel, while in other of these workloads, and as I said, we will talk in detail about most of these later, they use atomic operations, what we call the cross-device or system-wide atomic operations that allow the direct communication and synchronization between the CPU side and the GPU side. And this cross-device communication may heavily burden the kernel performance, as you can see, especially in some of the cases, the slowdown is pretty significant. However, when we also include the total execution time, because we are also including the data transfers, we are copying from the CPU to the GPU, and then from the GPU to the CPU in the traditional accelerator model, you can see that the view of this plot changes a lot, even for those benchmarks or those workloads where there was a huge overhead from the cross-device communication. We see that when we incorporate the data transfers into the equation, the idea of using unified memory can be very beneficial because it can hide the data transfers with kernel execution. So now we know the basics about the unified memory. We are going to continue showing some APIs that are necessary to implement collaborative computing applications. And that's what we are going to continue talking with a little bit more detail. We will start simple. We will start with potential implementations or possible implementation, collaborative or heterogeneous implementations using the traditional model, and then we would move to more sophisticated implementations using unified memory and these system-wide atomics that I already mentioned. So in the traditional approach, one thing that we can take advantage of for the CPU and the GPU to collaborate on the same workload is the fact that kernel launches are asynchronous. So what that means is that after launching the GPU kernel, we have the CPU threads free to do something else. So the CPU can do things after launching the GPU kernel. At some point, we can use this CUDA device synchronize to make sure that the GPU kernel finished, and then we can read the data, the output from the GPU memory to the CPU memory. But this is, let's say, the only possible way of doing fine-grained, let's say, collaboration between the CPU and the GPU in the traditional model without the unified memory. So with unified memory, it's possible to do even finer-grained collaboration, especially after the Kepler and the Maxwell architecture, since the Pascal architecture back in 2016, not only in NVIDIA GPUs, also with the HSA architecture, as I mentioned before. And the key advantages that enable this fine-grained collaboration is that the unified memory space is a coherent memory space. So that essentially means that any change that either CPU threads or GPU threads make on data that has been allocated in the unified memory is visible. These changes are visible to all other devices in the unified memory space. And also, and very important for communication, synchronization, and coordination of the execution across the different devices are the system-wide atomic operations. These could be the code for one generic GPU kernel that we launch from the CPU after having allocated the input and the output using CUDA malloc manage in the unified memory space. After launching the GPU kernel, because the kernel launch is asynchronous, the CPU can operate actually on the same data arrays that the GPU is operating on. And as you see, we can even execute atomic operations on those data. For APIs that you would need to use if you want to take advantage of the unified memory in CUDA, here you have these APIs for memory allocation, CUDA malloc manage, as we have seen before. It has essentially the same syntax as malloc or CUDA malloc, and this is the syntax of the system-wide atomic operations. As you see, it's also very similar to the syntax of the atomic operations to global or shared memory. It's just that they are adding this system qualifier at the very end. But these similar APIs also exist in OpenCL, since OpenCL 2.0, a way of allocating in the unified memory space that in OpenCL is called the shared virtual memory space. There are some specific flags that need to be used. For example, when we want to use atomic operations on the allocated data, and here you can see the syntax of the system-wide atomic operations that follows the syntax of C++11 atomic operations. For these atomic operations, we'll have to use this scope all SVM devices, because this way we refer to the shared virtual memory. And there are also Other programming frameworks like C++, AMP, that also takes advantage of the unified memory space that exists in HSA architecture. In this case, it's as simple as using malloc to allocate in this unified memory space. And there are also these C++11 atomic operations for all the unified memory space. And they are typically called platform atomics in HSA, as you can see on the slide. So let's start talking about examples that different programs that can take advantage of the collaborative execution. But before that, we are going to introduce what are, let's say, typical collaborative patterns that we can find in our collaborative execution. So let's very quickly recap on what's the traditional program structure. In the traditional program structure, think now about a GPU where we have multiple threads operating on multiple different data parallel tasks. These data parallel tasks might be composed by subtasks that are executed sequentially, as you can see on the slide, and we may have many of them. These are the data parallel tasks that we meant. These all together with the threads, GPU threads that run them or execute them can be considered a GPU kernel. And at some point, this kernel terminates. As you know, kernel termination is essentially a coarse-grained synchronization across all the involved workers in the previous kernel. And after one kernel finishes, it's possible for the CPU to launch a new kernel with new data parallel tasks, including different sequential subtasks. So how can we partition these across two different devices, assuming that these devices have different characteristics? They are heterogeneous. So if they are heterogeneous, it's likely that they need different amount of time, different latency to execute the same sequential subtasks. As you can see, this yellow subtask is faster on device 1 than on device 2, but at the same time, you can also see that device 2 has more workers than device 1. And for example, for this green task, this one takes longer. It's just a toy representation of this program and this subtask. So as you see, these green subtasks take longer on the device 1 than on device 2. At some point, when device 1 and device 2 finish with these data parallel tasks that have been partitioned across both devices based on what are their features and their characteristics. And obviously, we would try to do this data partitioning in a load balanced way so that both devices have more or less the same amount of work and they finish more or less at the same time. After the first kernel terminates, we have a coarse-grained synchronization. We start the next set of data parallel tasks, and they are again distributed over the two devices. So this is the data partitioning pattern. We now can think also, if we can partition data, we can also partition tasks, right? And we already know that some of the tasks are faster on one device, other tasks are faster on the other device. So one possibility is to apply a coarse-grained tasks partitioning, where we partition the tasks completely. Entire tasks are either executed on the device 1 or on device 2. So in this case, for example, the entire first kernel runs on device 2 because those data parallel tasks are faster on device 2. After the kernel, the kernel termination and the coarse-grained synchronization, device 1 executes the data parallel task in the second kernel. So this is what we call coarse-grained task partitioning. One thing to keep in mind here is that it might be possible for both devices to work concurrently as well. Why? Because this device 1 could be computing here the data produced by the other kernel in device 2 in an earlier step, in an earlier stage or iteration. And another way of doing this task partitioning is what we call the fine-grained task partitioning. In fine-grained task partitioning, we have we are going to choose the best device for each specific subtask. For example, these yellow tasks are faster on device 1, and green tasks are faster on device 2. So what we do is executing each subtask in the best possible device. The good thing is that it should be possible with unified memory. It will be possible to have like fine-grained synchronization across the devices. This is something that we are going to implement using system-wide atomic operations, as we will show later. And here you can see, well, the next set of subtasks. The next set of subtasks in device 2, at some point the kernel terminates, and then we go to the next kernel, and also with this fine-grained task partitioning inside the in the next kernel. Not to mention, I mean, there's no need to mention that these different collaborative patterns can coexist in the same program. We may have kernels where we prefer to do data partitioning because that's more appropriate for that specific phase of the computation of the program execution, while we may go for fine-grained or coarse-grained task partitioning in later or different stages of the program. We can do very quickly some analytical modeling of these collaborative execution patterns. Let's consider N, the number of data parallel tasks in the application. This TID1 is the execution time of subtask I by device 1, by a worker in device 1, for example, a CPU thread or a GPU thread. We have this TID2, that is the execution time of the subtask I by device 2 worker, the number of available workers in device 1, in device 2. We should also take into account that there exists some overhead due to the distribution and aggregation. And also for the data partitioning, we are going to consider this alpha, that is the fraction of parallel tasks assigned to device 1. As you can imagine, to device 2, we will assign 1 minus alpha. And also these SD1 and SD2 are the set of tasks or subtasks, depending on what's the task partitioning model that we are focusing on, that are executed in device 1 and device 2. So let's start with data partitioning. Remember that in data partitioning, we have to use this alpha, that is the fraction of data parallel tasks assigned to device 1. And as you can see here, the total, the total execution time, the way that we can estimate the total execution time for data partitioning, of course, considering this distribution and aggregation overhead factor. But as you see, the total execution time is proportional to the maximum of either the work performed by the device 1 or performed by device 2. So here in the numerator, you see alpha times n, that is the amount of work that is executed in device 1. This 1 minus alpha times n is the amount of work for device 2. We have here the sum of all the latency of all the tasks executed by the workers in device 1, same thing for the workers in device 2, and we divide both terms by the number of workers that we have in both devices. So here is the total execution time for the sequential execution. If we have multiple workers, we can parallelize the execution. And if we want to find what's the optimal alpha, we have to consider that the amount of work for both devices is exactly the same. And in that case, we can obtain this alpha optimal for which the workloads of device 1 and device 2 are balanced. So when it comes to modeling fine-grained task partitioning, here we have to consider these SD1 and SD2, which are respectively the set of subtasks executed in device 1 and in device 2. And because there is concurrent execution in device 1 and device 2, as you can see in this figure here, the value that defines what's going to be the total execution time is the maximum of the time needed to perform all the work in device 1 or in device 2. So that's why you can see here that this is the sum of all latencies of all tasks executed in device 1. Same here for device 2, and we divide that by the number of workers in both devices. And in the case of coarse-grained task partitioning, remember that here we don't distribute subtasks, but entire tasks. So in this case, the total execution time relates to the sum of the total work performed by device 1 or device 2. So that's why we have here the total latency of the tasks executed in device 1, device 2, and both are divided by the number of workers in device 1 and device 2. Then we add them, and we can obtain a reference, or at least an estimate of the total execution time. Let's now start discussing some examples, real examples that use these data partitioning. These partitioning strategies. We are going to start with data partitioning. We start with a very simple example, is a histogram computation. We are going to think about how to implement a histogram calculation simultaneously on both CPU and GPU with the traditional approach. So if we want to do so, what makes sense is to partition the whole input image, give a certain alpha to device 1, another 1 minus alpha to device 2. In this case, these devices are a CPU and a GPU. And what we need to do, and this is more or less like a reference code that we could need to use, is to first allocate input in both the image in both CPU memory and GPU memory. We also have to allocate separate histograms or subhistogram or partial histograms in CPU memory and in GPU memory. We launch CPU threads and GPU kernels to execute, to perform the computation, calculate these partial subhistograms. And at some point after the GPU kernel terminates, we have to move the GPU partial histogram to the CPU memory, and then have CPU threads merging both subhistograms. So as you can see, this is relatively cumbersome. It can be, let's say, easier program if we use a unified memory, but still using this approach of separate CPU and GPU histograms. But at least here we are saving memory allocations and also saving data transfers. But we can go one step further with the unified memory if we use the system-wide atomic operations, because in this case, we can have both CPU threads and GPU threads atomically updating the contents of the histogram. So that allows us to have a single histogram for the whole system in the unified memory. So this histogram residing in unified memory, and very, say, we can program this very easily by having CPU threads and GPU threads updating the and creating the same histogram at the same time. These, of course, may have some performance overhead, because these system-wide atomic operations are not going to be for free, but key advantage that we can already observe is that it's much easier and much more intuitive to program. Another interesting example are Bezier surfaces. We already talked about Bezier. We talked about Bezier lines in the previous lecture, dynamic parallelism. Here, instead of talking about lines, we talk about Bezier surfaces. It's essentially the same concept. In this case, we want to create a surface based on a net, a two-dimensional net of control points. As you can see here in this example, we have a 4x4 net, 4x4 net of control points. These Bezier surfaces use Bernstein polynomials. We consider in this example a bicubic surface where m and n are equals to 3. These are the control points that we have, in both dimensions, and this is the way that we compute the points of the surface based on the control points. We may have a lot of points to compute in this Bezier surface, so it might make sense to have multiple, let's say, two devices, a CPU and a GPU, collaborating in order to obtain some performance improvement from this collaboration. Because this is kind of a regular workload, it's pretty likely that we can obtain good performance with a static distribution. Of course, we would need to profile in advance the workload in order to figure out regarding the total amount of compute that we have, and regarding what's the compute power of CPU and GPU. We would have to find probably with offline profiling what's the best alpha, the fraction that's going to be assigned to the CPU or to the GPU, but that's certainly possible, and it's going to produce a good performance result. This static distribution could be something like that. We have the whole surface, we divide the whole surface into tiles, and we assign different tiles to either CPU threads or GPU blocks. Without unified memory, as I said, we need to know what's the fraction of points that are the points in the surface, I mean, that are going to be calculated by either CPU threads or GPU threads. But once these optimal partitioning has been found, we just need to first allocate double allocation in CPU and GPU memory, of course, launching CPU threads to perform computation on the corresponding tiles. Same thing for the GPU kernel. At some point, we synchronize, we copy the corresponding part of the GPU from the device memory, from the GPU memory to the CPU memory, and then we are done. Following this approach, we implemented these Bezier surfaces for an NVIDIA Jetson TX1. Remember that this is a heterogeneous platform with 4 ARM CPU cores and 2 GPU cores. We consider here a Bezier surface of 300 by 300 points and 4 by 4 control points. And here in these execution time results, on the x-axis, you can see what's the alpha, the percentage of tiles that are assigned to the CPU. And as you can see, we can obtain certain performance improvement from having this collaboration between CPU and GPU, 17% speed up over the GPU only version in the best case. If we have unified memory, easier programming because we don't have to take care of data transfers, for example, and in this case, this allows us to, so the unified memory allows us to even have a dynamic implementation where the distribution of the tiles over the CPU threads and the GPU threads is dynamically done. As I said in the beginning, these Bezier surfaces are relatively a regular workload, but for workloads that are more irregular, that have more irregular computation, this dynamic implementation can be a very good way of balancing the workload across the different devices. And this is possible after, so in Pascal and later NVIDIA GPU generations, thanks to the use of the unified memory and the system-wide atomic operations. And here you can see how a possible implementation of this communication and dynamic distribution based on the use of system-wide atomic operations. This is the code, the piece of code that we would have in the GPU kernel. We have some sort of while loop that is always looping, fetching a new tile, computing on the tile, writing the results, and they go again to a queue where all these tiles are available, and the execution of the tile or the computation of the tile later proceeds. Observe that in order to fetch a new tile, what we do is just updating this tile num, that is a variable that resides in the unified memory and tells us what's the next tile that is available for computation. So this system-wide atomic add is just executed by a single thread in the thread block. This one shares the tile ID with all other threads in the thread block using shared memory, synchronizing here, and after that the threads start computing the points of the output surface. Of course, they have to check when the number of tiles is done, when all tiles have been consumed, and in that case, break the loop. And by doing this, so implementing Bezier surfaces in this way, we ran experiments on an AMD Kaveri, that is a CPU, GPU integrated chip that contains 4 CPU cores and 8 GPU cores. And as you can see, data partitioning improves performance significantly, up to 47% improvement over the GPU-only version. Here on the slide, you can see execution time, how it changes when using 1 CPU, 2 CPU threads, 4 CPU threads, or the GPU plus the number of CPU threads. And in this particular case, because this Bezier surface is relatively compute-bound operation, it really benefits from having more workers operating and computing the output surface. Another interesting example is matrix padding. Matrix padding is an extremely useful primitive, very simple one, but extremely useful primitive for different use cases, for example, memory alignment or transposition of a square matrix near square matrices. So as you can see here, it's essentially consists of adding extra columns to an existing matrix, right? So in total, we would, in order to perform this padding, we would need to allocate a little bit more memory than the memory that is actually necessary. But then after the padding operation, as you see, the extra column appears in the right place. So traditionally, this can only be performed out of place because as we start shifting some of these rows in order to keep this extra column empty, we have to overwrite positions in memory that are highly addressed, right? So for example, these 5, 6, 7, 8, 9 has to be shifted one position to the right, to, let's say, higher addressed memory locations. So it's usually so we have to be usually very careful when performing this operation because we can overwrite data. So that's why it was typically performed out of place. And that's actually our first implementation on the NVIDIA Jetson TX1. What we do is partitioning the matrix statically across both devices. We give one part of the matrix to the CPU, another part of the matrix of the GPU. We perform the padding operation, shifting rows, and so on, and then we merge both parts. And here you can see, but for a matrix of 4,000 by 4,000 and padding of one extra column, we obtain up to 29% speed up when finding the optimal distribution of workload between CPU and GPU. With unified memory, because both CPU and GPU have access to the same memory space, and they can also synchronize using system-wide atomic operations, it's possible to do in-place padding. And these kind of in-place operations are pretty important for devices such as GPUs that are not so rich in memory. Even the latest GPUs are still way behind the memory capacity of the typical memory capacity of CPUs. So in-place implementations are pretty useful for heterogeneous devices in general and for GPUs in particular. So let's assume that we have our original matrix in the coherent memory space. We also have an array of flags that is going to be updated by either the CPU thread or the GPU threads using system-wide atomic operations, and then both CPU and GPU have some temporary location. In the case of the CPU, it will be the different cache levels of the CPU. In the case of the GPU, it will typically be shared memory and or registers. So this is what we want to obtain, the matrix after performing the padding operation. But this is how it's going to look in memory exactly, because remember that memory is linear. So that's essentially how the data is going to be mapped onto memory. So let's just start moving rows from one position to another position. And right after one row has been saved in the GPU temporary location, it will be possible to inform other workers that they can overwrite the original space for that row. So, for example, here we assign this blue row to the CPU. So the CPU starts loading the row into the temporary location. Same thing for the GPU. For example, this orange row has been assigned to some GPU thread block, for example. Same with other rows. At some point, when the CPU has saved the entire row, it can signal the rest of workers by updating the corresponding flag. And right after that, it starts writing onto the final destination. So the fact that the CPU thread, in this case, updated this flag means that the rest of workers here know that they can start writing as soon as possible in the final destination, in this case for the orange row that was assigned to a GPU thread block. And this is how essentially we are going to perform the whole operations, as threads or GPU thread blocks or CPU threads save the data of one row into the temporary location. They can update the flags, and then they can write into the final destination. So these adjacent synchronization using system-wide atomic operations makes possible in place implementation of, in this case, the padding primitive. And here you can see some results using this sort of implementation on the AMD Kaveri. Here you see the results for padding operation for different matrix sizes and different combinations of blocks and threads, because this is on an AMD Kaveri that uses OpenCL. We talk here about work groups and work items, and you see how the performance may improve as we increase the number of workers. We have collaboration of the GPU and CPU, but these also may depend on what's the specific configuration. In summary, padding is a memory-bound workload, so not always is going to get benefit from having more threads computing, because in the end is the access to memory what is actually more important. The exploitation of the memory bandwidth, what is more important for the performance of these memory-bound workload. But as you can see, we obtained quite interesting performance results with this in-place implementation, very close to the measurements with GPU stream. And here you have a different workload. In this case, it's string compaction or filtering. It's kind of similar to padding, but in this case, instead of moving the rows like by a fixed amount that is just determined by the number of columns that we want to add to the matrix, here in string compaction or filtering, we are filtering. So that means that we are removing elements. For example, we want to remove all elements that are 0 in this input array. So that is going to be input dependent. So the number of elements that one particular worker, either a CPU thread or a GPU thread or a GPU thread block, have to move to the output depend on the specific input. And because of that, it's important to, so it's necessary and not only to signal other workers when some particular data has been saved in the temporary space, but also propagate the local reduction result. So if these, for example, 3 or 4 values here were assigned to thread 0, and this thread 0 is going to filter out this 0 here and only copy these 3 elements to the output, the next worker, let's say thread 1, needs to know where to write the corresponding values, these 3 values, for example, that were assigned to it. And to do so, we have to communicate this local reduction result. We can already see here some performance results on the NVIDIA Jetson TX1. In this particular case, for this alpha, we obtain up to 25% speed up. And similar results on the AMD Kaveri, in this case, up to 82% performance improvement over the GPU version, as you can see on the AMD Kaveri. So these were some examples of data partitioning workloads. Let's now talk about coarse-grained task partitioning workloads. And we are already quite familiar with the first one of them is breadth-first search. Remember that in the graph search lecture, we talk about BFS, we talk about implementing it using a top-down approach. We even talk about this hierarchical kernel arrangement where we have different kernels depending on what size of the frontier. We call them kernel 1 and kernel 2, and we even discussed one way of avoiding kernel relaunch by using interblock synchronization. We are going to recap on all of this today. Another thing that we already know is that very small frontiers and they utilize GPU resources, and in this case, it makes sense to have a collaborative implementation as we have discussed earlier. Here you can see another figure to represent this collaborative implementation of BFS. As you can see, small size frontiers are assigned to the CPU. At some point, the size of the frontier goes larger beyond a specific threshold. So we start computing on the GPU side, and then maybe probably at the end of the execution, when again the frontiers start shrinking, we return the control to the CPU and continue computing on the CPU. This is possible to implement even without unified memory. We need to do, of course, explicit memory copies using CUDA and copy, but this is more or less the skeleton of the host code where we control what's the size of the frontier. We will continue executing iterations as the size of the frontier is not zero. If the size of the frontier is below the threshold, then we launch CPU threads. If it's above the threshold, then we launch GPU kernel. Important observation here is that we need to copy all necessary data, in particular the queue and synchronization variables, from the host memory to the device memory prior to the execution of the GPU kernel. And then after the execution, when the GPU kernel terminates, we will have to copy them back to the CPU because we assume that they are going to be the CPU threads that will continue the execution. And as you see, we will typically have this in this, let's say, more naive implementation. We would typically have the CPU controlling what's the progress of the iterations, and every new iteration will have the CPU thread, the main CPU thread, deciding whether we launch more CPU threads or we launch a GPU kernel. With the unified memory, it might be easier to program because there are no explicit memory copies, but we would proceed in a similar way. So in this case, what we are going to do is launching the kernel for every new frontier if the size of the frontier is above the threshold. The problem with this approach, even if we are using unified memory, is that there is a high overhead of kernel relaunch, especially in a kernel like BFS that is mostly data movement. There is not so much computation because essentially what we have to do for every node in the frontier is to check what are the neighbors and see what's distance to this. So how far these neighbors are, but in the end, there's not so much computation. And that's why we can observe these interesting results here with normalized execution time for many different graphs, as you can see in the x-axis, and also many different CPU, GPU collaborative configurations where we either use a single CPU, like a CPU with 2 cores, or we use the CPU or the GPU with different threshold. If you look at the details here, you'll see that this threshold might be 64, 128, 256, or 512. And one thing that we can clearly observe here is that there is a direct relation between the number of GPU kernel calls, the number of times that we relaunch the GPU kernel, and the total execution time. So this high overhead of the kernel relaunch makes the collaboration impractical. So in these kind of cases, instead of terminating the kernel and starting a new kernel for every single iteration, it makes sense to go for this implementation with persistent thread blocks, where we avoid the kernel relaunch. Remember that we already covered this in the graph search lecture, and here we even discussed how the code inside the GPU kernel would need to look like to perform some global synchronization at the end, global synchronization across all the thread blocks at the end of each iteration. And here you can even have a simplified code of this global synchronization, how to do it for all the different persistent thread blocks that are collaborating on the execution of the breadth first search algorithm. I'm not going to go into discussing this code in detail. If you want to understand it completely, please go to the corresponding graph search lecture. One interesting observation here as well is that this code was originally created for only, say, the GPU side for synchronization of the thread blocks running on the GPU, but with by using system-wide atomic operations, it's also possible to have the CPU threads synchronizing with the GPU thread blocks. Just simply need to use system-wide atomic operations here instead of regular atomic operations to global memory. So in this collaborative implementation, we are going to use CPU or GPU depending on the size of the frontier, and we can launch either CPU threads or GPU kernel. And when we launch the GPU kernel, it's possible for us to keep the GPU threads, the GPU thread blocks running while the frontier size is over the threshold. And we can clearly get some benefit from that, because we are avoiding the problem of relaunching, I mean, the overhead of relaunching kernels. And that's essentially the implementation that we use for these results that you have already seen earlier. But if we have even more fine-grained collaboration, we really have system-wide atomic operations, and we have the unified memory post Pascal or the HSA architecture. It's possible to have CPU threads, GPU threads running all the time and just working when they detect that the size of the frontier is in the corresponding range, right? And at the end of the execution, we just do this CUDA device synchronize, and we are sure that everything has been done. Actually, this implementation using system-wide atomics for communication across CPU threads and the GPU kernel gives us the possibility of going one step further. If we have very, very, very large frontiers, it could be possible to have CPU and GPUs working at the same time on the same frontier. So we evaluated this implementation on the AMD Kaveri, and here you can see results for many different graphs and also different combinations of CPU, GPU, and collaborative implementation of CPU or GPU. And as you see, obtain up to 39% faster performance than the GPU-only version for some of the graphs. When the graphs are very, very large, most of the time the frontiers are very, very long. And in that case, almost in all cases, almost in all iterations, we are going to choose the GPU. So there is essentially no difference between the performance of the GPU version and the collaborative version, as you can see. And here you can see some more results on the AMD Kaveri. In this case, it's not VFS, it's SSSP. It's a single source shortest path. It's a very similar algorithm, just with a little bit more of computation. And here for 3 different graphs, we can see that there is up to 22% performance improvement over the GPU only version. So these are our examples for coarse-grained task partitioning. Now let's talk about some examples for fine-grained task partitioning. The first one that we are going to discuss today is the random sample consensus algorithm, or RANSAC. That is a popular algorithm to generate models of something happening in our input data. In particular, we use it for ego motion compensation and moving objects detection algorithm that was used by an Exapod robot. And you know, this robot is using uneven terrains with strong ego motion. So in the end, this robot was created for rescue scenarios. So it really needs to identify when we have a moving object that might be, for example, a person that needs help. And the way to compensate the strong motion due to the terrain is to generate a model of the image of the optical flow vectors of the image. And this model is going to represent the background, because the background is moving the same way as the robot is moving, right? So the optical flows, the optical flow vectors of the background represent the movement of the robot. So if we know what's the movement of the robot and we know what's the movement of the background, we can subtract it from the image, and this way only the flow vectors that belong to the moving object, to the maybe the person that needs help, so they are going to be the ones remaining after removing the vectors from the background, and this way we can identify the moving object. And here you can see one example of how in this image we have a huge amount of optical flow vectors that correspond to the background, because the camera is moving here while other flow vectors represent the moving object. And by using this algorithm, it's possible to identify where the moving object exactly is. So to generate this model of the optical flow vectors in the background, we, as I said, use RANSAC. And RANSAC is like an iterative algorithm where in every single iteration, there is first a fitting stage. In the fitting stage is just to pick at random two flow vectors, two optical flow vectors, and generate the model from them. After this model has been created, we have to evaluate it, to compare it to the real optical flow vectors and see how accurate the generated model is. And after performing this comparison, we choose what's the I mean, if the current model is better than previous models, in that case, we update the best model so far. And there are some interesting observations here. The first one is that these different stages have more or less data parallelism. As you can see, there are phases that are inherently sequential, like the fitting stage or the comparison to the best model, while there are other, or more essentially this evaluation stage that is a SIMD phase. There is a lot of parallelism here because in the evaluation, we are comparing the optical flow model to all the real optical flow vectors. So this is very suitable computation for a collaborative execution, and that's essentially what we did in our collaborative implementation. We assign the CSD phases and sequential phases to CPU thread. We assign the data parallel phases to the GPU thread blocks, but also, we realized that the iterations were independent, so it was possible to execute multiple iterations in parallel by assigning them to multiple GPU threads, multiple GPU thread blocks, and CPU threads, as you can see represented here in the slide. So in summary, we have discussed like three important collaborative patterns: data partitioning, coarse-grained task partitioning, and fine-grained task partitioning. And if you want to learn more about these these collaborative execution patterns, I can recommend you to take a look at our paper, CHAI Collaborative Heterogeneous Applications for Integrated Architectures, and also the CHAI Benchmark Suite that contains collaborative implementations for CPUs and GPUs, and also for FPGAs, as we are going to show you soon. The CHAI Benchmark Suite contains, as I said, different benchmarks from the three different patterns, and also quite interestingly, there are versions, different discrete and unified versions written in CUDA, OpenCL, and even C++ AMP, and even some versions that can be used in the Gen 5 GPU simulator. So this is a web page from which you can access the paper and also the repository. And if we take a look about the details. Here you have the complete list of the benchmarks that we have, like Bezier surface, candidate detection, histogram. As you can see, these are essentially the different use cases or the different examples that we have discussed in the previous slides. And you can see in this slide also the diversity of the benchmarks in terms of the partitioning granularity. For the data partitioning benchmarks, in some cases we have more fine-grained granularity because the tasks are smaller, assigned to CPU threads or GPU thread blocks, or maybe they are more coarse, like for example in candidate detection, where we are assigning whole frames of a video to either a CPU thread or a GPU thread block. And also different partitioning strategies. We can either partition the input or the output. Some of them use atomic operations, some of them don't. And these system-wide atomic operations might be used for computations, for example, in the histogram calculation, or might be used only for synchronization across the workers on the different sizes. And more or less similar information you can find here for task partitioning, either fine-grained or coarse-grained. And even more figures here about the diversity of the benchmarks. This is the varying intensity in the use of system-wide atomics. I think that this can be pretty interesting for people interested in optimizing these sort of operations. You see that there is a interesting variety here across the different benchmarks, and also diverse execution profiles. These were results obtained with the AMD profiler or an AMD Kaveri, and you see how the different benchmarks have different occupancy values. They have different rates of utilization of the ALUs, utilization of memory, and also heats in the cache hierarchy. As you see, quite diverse execution profiles. So we use these benchmarks to analyze in this case, we use an AMD Kaveri, as I said before, with 4 CPU cores and 8 GPU cores. In this case, we use the unified and distributed versions implemented in OpenCL, and you see for all CHAI benchmarks, the comparison in the kernel execution time. We observed that for data partitioning workloads, the kernel execution time is comparable. But in some cases, we see that the unified version is slightly slower due to the use of system-wide atomics. In the case of the fine-grained collaboration, one good thing of the unified kernels is that because of this fine-grained collaboration, they can exploit more parallelism, and there is some, a kernel execution time saving, as you can see for these 3 benchmarks, while the coarse-grained collaboration also has some improvement in the unified version because it can avoid the kernel launch overhead. Performance improvement from using the unified memory in this AMD Kaveri that is integrated CPU and GPU in the same chip. It goes even further if we take into account what's the cost of the explicit data transfers in the discrete or the traditional model, because we have to copy from the CPU, the area of the memory that is assigned to the CPU from the area of the memory that is for the GPU. We have to do that for input data, and for output results as well. The unified memory versions avoid completely this copy overhead. Only one thing that we observe is that the SVM allocation, the allocation of the unified memory space, takes longer, and these AMD Kaveri, these were results already generated like 5 years ago. So this SVM allocation might have improved and now might be more optimized in newer architectures. Because we also have C++ AMP versions, and these C++ AMP versions also run on the AMD Kaveri. We also perform a comparison of the unified versions in OpenCL and the unified versions in C++ AMP. As you want to learn more about all these benchmarks and all these experiments that we run back then, I can recommend you to take a look at that paper. And if you want to keep learning about these sort of workloads on heterogeneous systems with CPUs and GPUs, I would definitely recommend you this book, and in particular, Chapter 8, Application Use Cases with Platform Atomics, that are how the system-wide atomic operations are called in the HSA architecture. But this idea of the collaborative execution does not only apply to CPUs and GPUs, it also applies to other heterogeneous devices. And there have been a lot of activity in that regard in the let's say, a field of heterogeneous computing with CPUs and FPGAs. And here you can see some a motivation slide. This applies to a system with CPU cores and also some FPGA device. Traditionally, you have to have, same as in an heterogeneous system with CPU and GPU, in a heterogeneous system with CPU and FPGA, you have to perform allocations, you have to perform explicit data copies, and this was pretty cumbersome for programmers. So that's why different vendors started to create, to design coherent interfaces. Good examples are these CAPI2 and OpenCAPI, the coherent accelerator processor interface for CPUs and GPUs developed by IBM and other vendors. Good thing of this approach is that it's possible to have just one coherent version of the data, and that CPU and FPGA can tightly collaborate on the workload, saving many data transfers. But it's not only IBM, also Intel with their Altera FPGAs started to enable these unified memory space via programming with the OpenCL SDK. And actually for this sort of platform with a CPU, typically a Xeon CPU, as you can see in the table, and an FPGA, we actually tried two different platforms with two different FPGA chips. We implemented the CHI benchmarks on these platforms and also analyzed what were the benefits of collaboration in this kind of CPU plus FPGA heterogeneous system. In this particular slide, you can see the case study for cutting edge detection. As you may see in previous slides, we have two different versions of cutting edge detection in CHI benchmark suite. We have one that is data partitioning, and the other one is coarse grain task partitioning. So that's why for the two FPGA-based systems, we have here a comparison of the execution time of single device execution, either on CPU or on FPGA, and the collaborative execution, either using data partitioning or using task partitioning. As we can see, there is a clear performance improvement from the collaborative execution, and in this particular workload, we see that the total execution time is kind of similar for both the data partitioning and the task partitioning strategies. We also did similar analysis for random sample consensus for RANSAC. We also have two different versions of RANSAC. RANSAC, one is data partitioning, the other one is fine-grained task partitioning. In this case, we observed that the task partitioning exploits the disparity in nature of the tasks, so it adapts better to this specific workload. Remember that here we have a clearly SysD phases, completely sequential, while at the same time clearly massively parallel or SIMD phases. So by specializing the devices for computation, CPU side running the sequential part, while the FPGA running the data parallel part, we can here observe some interesting performance improvement, even if we explore like all different possibilities, all different alphas for the data partitioning. And here you can see, this is the paper, link to the paper, and also link to the CHI CPU FPGA benchmark suite. And this is another interesting work that also uses the CHI benchmarks, but in this case, it's it's like a framework for automatically deciding optimizations for OpenCL on FPGAs. I mentioned earlier CAPI, Open CAPI. This is something that some people in our group that have also worked with in concretely or postdoc Gagandeep Singh during his PhD thesis. He worked on this kind of system with a Power 9 CPU and an FPGA board with either DDR4 memory or HBM memory, both connected with the OpenCAPI interface, and he used this system to create an accelerator, a highly optimized FPGA-based accelerator for weather modeling. Here you can see some figure representation of this narrow application framework with the narrow accelerator with the different processing engines or processing elements with some on-chip memory, and from there access through the HBM memory controller to two HBM2 stacks. But at the same time, this FPGA is connected through the coherent interface to the host power system. And here you can see, one version of the paper that was, or this work that was presented at FPL 2020. This is another shorter version of the paper that also includes some new applications such as pre-alignment filtering in bioinformatics. But neither this OpenCL in Intel nor OpenCAPI are the only frameworks that provide say coherent interfaces across different devices. More recently, we have learned about the Compute Express link that is also an open industry standard, same as OpenCAPI, an open industry standard interconnect that offers high bandwidth, low latency connectivity between the host processor and devices such as accelerators, for example, GPUs or FPGAs, but also other devices and even memory buffers. This is currently under development as far as we know, and hopefully in the near future, we'll have access to these kind of systems, and we can evaluate what are the potentials of this new coherent interface. And hopefully soon we will have access as well to NVIDIA Grace CPU and the Grace Hopper super chip. Here you can find the links to a couple of announcements. Apparently, these NVIDIA Grace CPU and Grace Hopper super chip are going to be soon used also in supercomputing centers, and they are, as I said in the beginning, very interesting devices for collaborative execution due to their high compute capabilities, but also the fact that the ability to communicate quickly through a coherent interface. And I mentioned earlier that this Grace CPU superchip contains this 900 coherent interface. In particular, let's say the CPU superchip is only CPU. As you can see in the image, it has up to 144 ARM version 9 CPU cores, and apparently it's going to have a total bandwidth of 1 terabyte per second for with LPDDR5X memory with ECC. And this is a picture of the Grace Hopper superchip with the Hopper CPU, with the Grace CPU and the Hopper GPU, and in between we have this 900 gigabyte per second coherent interface. For sure, it will be pretty interesting to evaluate collaborative execution patterns on this architecture. So, key takeaways of this lecture: collaborative computing. We have the possibility of having several devices collaborating on the same workload and having the most appropriate cores for each workload exploiting heterogeneity. We have seen that it's easier to program these heterogeneous systems with unified memory or shared vector memory, as is called in the HSA architecture, because they provide GPU, CPU, or GPU, FPGA, or maybe other devices, memory coherence, and system-wide atomic operations. In the case of GPUs, this happened since the NVIDIA Pascal architecture and also since the HSA architecture, enabling this fine-grained collaboration that is especially promising for devices that are tightly integrated, heterogeneous devices that are tightly integrated, either in the same chip or in the same package, sharing the same off-chip memory, or potentially as well for these devices with high bandwidth coherent interfaces. We have talked today about CPUs, GPUs, FPGAs as example of heterogeneous devices and examples of heterogeneous devices that can benefit from collaborative execution, or the workloads running on them can benefit of collaborative execution, but they are not the only heterogeneous device that we can find in a system nowadays. We see in the last few years the rise of new trends such as processing in memory. We are delivering another course on processing in memory systems, where we discuss, and investigate about different processing in memory architectures. Some of them are already in the market, others have been prototyped, and others are, let's say, research proposals, but pretty promising research proposals. So if you want to learn more about collaborative execution and also about processing in memory, this course can be a good recommendation to you. Here you have same links for the current course or current heterogeneous systems course, but these are not the only courses that we are delivering, very specialized courses that you can find in our websites and in our YouTube channel. Different courses about SSDs, memory systems, bioinformatics, hardware, software co-design, etc. And you can find all these resources and even more from the bachelor's and advanced computer architecture courses in Honor Moodle lectures in YouTube. So this is all for today. Thank you very much for your attention. I hope to see you all in the next lecture of this course.